myself as more Arunachali. I did my schooling from there itself. Then we shifted to Guwahati. I did my higher studies, then came to Roorkee, did my PhD. Then I was in an oil company for around 2 years, which is as a petrophysicist, Weatherford International. Around 5 years, I worked with ISRO in IIS Dehradun, and your previous lecturer, Bhaskar Nikam, yeah, he was one of my colleagues there, and we are a very good friend. Actually, we are batchmates. And for last 6 years, I am at IIT Roorkee, and I'm working here, both in terms of teaching as well as research also. And fortunate that yes, I have a good team of research scholars, including Sashikant, and who are producing some really nice research work, which we are trying to address few of the important research questions. So today I'm going to present a little glimpse on what is Glacier and what is mass balance and how a mass balance can be indicator of glacier health. Rather, I'll more focus on the techniques of mass balance and what type of techniques are there that we use for mass balance. This is a little bit long lecture, so I think I have around 83 slides. So let's see how quickly I can finish. At the same time, how nicely we can communicate with each other, and maybe it could be learning lesson for both of us. I'll also learn something from you, and you all can learn something, whatever I can tell you. Okay. Yeah. To start with, I would first want to acknowledge whatever I am going to present today, and all my papers on mass balance to a few of the persons. Number one, it's Professor Anil Kulkarni, who is from IIT Bangalore, with whom I am doing one research project, imprint project, and we have some 4 pieces research scholars shared. Majority of the work that I'll be showing here are contributed by 2 of my research scholars, Jaidev Kumar Tharpure and Kansha Patel. So thanks to them also. I have a collaborative research HICOM project with NCPOR Goa, where Dr. Thambal Melot and Dr. Parmanand Sharma, they are my collaborators. So yes, the work that I'm going to show, few of the works that these are from this particular project also. So I must thank the sponsors. And then the last one is the bottommost paper. This paper is by Bhanu Pratap, who is presently working in NCPOR. DP Dobhal, who is a very famous glaciologist from Wadia Institute of Himalayan Geology. And Rakesh Bhamri, he is a very famous glaciologist and cryospheric scientist. So they have published one paper on 4 decades of glacier mass balance observation in Indian Himalaya. So yes, some glimpses or some information are from this particular review paper also. It's a nice review paper. Apart from that, there are many important papers which you can always browse through. You can go through any of these authors' contribution. You will get nice information apart from many other informations. Okay. So if you look at the distribution of glaciers, how glaciers are distributed, you would see that like New Guinea, it has got 3 glaciers, Africa around 6, New Zealand around 1,160 glaciers, Scandinavian countries around 2,940 glaciers, Central Europe has some 4,000 glaciers, South America, the number increases. If we come to North Asia, it goes beyond 75,000. If we again move to Antarctica, it's around 75,000. Central Asia, it's more than 1 lakh, and North America, it's around 1,30,000. And if you go to Arctic, then maybe we have even more, 3 lakhs. Okay, so you could see that what is the global distribution of glaciers. Now, there are lots of news and lots of media attention which came on glaciers. Like recently, you might have heard about the Chamoli incidents, where there was a rock avalanche, rock and snow avalanche, and a huge chunk of ice actually fall down, which created artificial flood in one way, and it destroyed 2 hydropower projects, and some 200 people are missing. So similarly, there are many news which are coming up. Even many states, they are complaining that the hydropower projects or irrigation projects, like big reservoirs which are created to store all this waters for both hydropower as well as irrigation, now the level of water are going down. And if you look at why the level of water are going down, either the source could be rainfall, it is decreasing, or it could be snow melt, which is decreasing. Rainfall, if it is constant, so it means the snow melt is decreasing. So again, it's one more important issue to find out the health of those glaciers, so that we can say that after maybe some 20 years or 50 years, what will be the situation in terms of water availability, and how we need to cope up with this water availability, whether it is less or it is more, or it is sporadic or it is regular. Okay. To start with, what is glacier? So when we talk about glacier, first of all, we should know what is a glacier. So glacier, it's a huge body of ice, okay, with some amount of snow, which is formed on any land surface. and due to its huge weight, okay, due to its huge weight, it starts to move under its own weight under the influence of gravity. So there are glaciers as well as landslide which moves under the influence of gravity, and glacier is that one where you have got huge amount of a huge chunk of ice or snow which moves due to gravity. So next question comes that where do we find glaciers? Glaciers we can find in two places, okay, two locations. Geographically, you can find glaciers in two locations. One is higher altitude, second is higher latitude, or combination of both. How? So if you see condition in India or Asia, so we if you see the glaciers in Asia or in India, these are mostly located along the tropic. Okay, it's located along the tropic or Tropic of Cancer, and where the height is quite high. So because of the Himalaya, okay, because of the uprising of Himalaya. So here the glaciers could be seen at 3,800 meters or above. The snout of the glaciers are mostly at 3,800 meters, and above that 3,800 meters you could see glaciers. Okay, but if you go to pole, okay, if you go to pole or mid latitude, so in poles, even if you go to like Norway, okay, Norway or any other such countries, Scandinavian countries, you will find that glaciers could be seen. These are found at sea level. We don't need elevation, rather we need sea level. In sea level itself, glaciers could be seen. So it means either we can have glaciers in high altitude, like in Himalayan condition, or we can have glaciers in high latitude. Okay, high latitude means towards the pole. So there also you can find glaciers. So high altitude and high latitude, or combination of both. Okay, then the next question which comes to our mind is that how much percentage of fresh water is locked up in glacier? If you look at the freshwater supply of the world, around 75% of the world's supply of fresh water is locked up as glacial lake, and therefore it is that much important, because if we need to survive or sustain both for agriculture, drinking purpose, or all other domestic and important purposes, we need fresh water. So how these glaciers form? So initially what happens, that there will be snowfall, which are basically snowflakes. Snowflakes are very, very beautiful if you look at under microscope, and they are very fluffy. It means when snow falls, there are lots of void spaces in which air is trapped. So when this snow basically metamorphoses or it tried to compact, when compaction takes place, so these the edges are broken down, it forms granular snow, then it converts to firn, and then it finally converts to glacial ice. So in that process, in that compaction, the air which is trapped inside will be gone, as well as the spikes or beautiful spikes which are formed in snowflakes, these are gone. It actually metamorphoses and it forms firn and then glacial ice. How do glaciers move? There are two basic types of movement. One is basal slip, another is plastic flow. What is basal slip? So glaciers, mostly in case of temperate condition, it means like Himalayan condition, Andes condition, or Alps condition. So in those conditions, what will happen, that those glaciers, at the base of the glacier, there will be melting, okay, because of the enormous pressure which is exerted by this huge chunk of ice with the rock which is at the base. So there will be a little bit of friction, and because of the friction, there will be a little bit of melting. This melting triggers, it acts as a lubricant, and because of that, the glacier can move by basal slip. So it is basically slip. Second is plastic flow. Plastic flow means when we go to poles like Antarctic or Arctic, in mostly in Antarctic condition, there won't be any slip. Rather, it will flow like a plastic. As you might have seen many videos of lava, okay, how lava moves. It moves in a plastic form, isn't it? So there will be plastic deformation, and then by plastic deformation, it can move. In between, you can have both combination of basal slip as well as plastic flow. Yeah, so this is one more sketch which shows that how snowflake, it converts to granular snow, then firn, and then finally glacier ice. So in that process, all those beautiful edges are broken down and it becomes more and more compact. So why we are more concerned about glacial retreat or glaciers? So you see, the retreat of glacier is in all around the world is a concern, because it's directly or indirectly it is affecting the Earth's inhabitation, and also it contributes to sea level rise. So if like all the glacier stored water is released into a river, ocean, because of melting, so what will happen, that our ocean level will increase by few meters. If it increase by few meters, you just can imagine that most of the islands countries will be drowned. Even the coastal places will be drowned. So that is one of the major concern. Secondly, it also impacts the heat budget, because The glaciers as well as snow-covered area, these have got very high albedo. What is albedo? Albedo is the gross reflectance of EMR or electromagnetic radiation from 0.34 to 2.5 micrometers. So in that whole range, how much radiation is outgoing and how much is incoming. That ratio is albedo, which is a dimensionless property. Okay? More importantly, the Himalayan glaciers are the source of numerous rivers that accommodate the water needs of millions of population in Asia. So if you look at Indian condition, there are so many people downstreams, okay, in Indo-Gangetic and Brahmaputra plain. These people, it depends highly on those rivers which flow from that particular area, and these rivers are mostly glacier fed. Okay, there is a huge contribution from rainfall as well as base flow, no doubt about that, but even the glaciers feed them during lean period. It means during the winters. Okay? Therefore, it's very important that we study the Himalayan glaciers. Not only it is essential for climate change, but it is also essential for sustainability and utilization of water resources. And there are very few people, very less chunk of people all over India who are working on glacier. Okay. If you look at this particular map, which I have actually, I got it from the paper by Bhanu Pratap and team. So here they have shown that where exactly the glacier mass balance studies have been done. Okay, where exactly mass balance studies has been done. As the word says, mass balance. Okay, there are two words, mass and balance. So what is mass? Mass means how much amount of water equivalent is there in those glaciers. Water equivalent, meter cube per year. Okay, meter cube per year, how much water is contributed. So that is the mass. And balance means how much amount of accumulation is taking place in winter and how much melting is taking place in the summer. So if we compare that, if you make a budget between the accumulation and ablation, so if that budget is positive, then it is positive mass balance. If that budget is negative, it means it's a negative mass balance. Negative mass balance means the health of the glacier is actually in a poor condition and we will have water scarcity in future. If it is positive, that's a good sign for now. Okay. So if you look at distribution of different type of mass balance studies, so you could see that glaciological method based mass balance study, which is a field based study, there are around 15 studies which are conducted all along Himalaya. So 10 glaciers in the Western Himalaya are studied by glaciological method. 4 glaciers in the Central Himalaya are studied by the glaciological method, and 1 in the Eastern Himalaya is done by the glaciological method. Fine. Second is the hydrological mass balance process. So this is one more method of doing mass balance studies, which we will discuss subsequently. So only Siachen Glacier is studied using hydrological mass balance. Okay, only Siachen Glacier is studied using hydrological mass balance till now. People are trying in some other areas also. Maybe in future we will get some manuscripts or research papers. Geodetic method. Geodetic method means where we use DEM, digital elevation model. So it is more desktop job. So geodetic method is applied in many glaciers. Now actually there is a very good paper which came out recently in one subsidiary journal of Nature, where Gulab Singh and his team along with Professor Anil Kulkarni, they have published geodetic mass balance for a major part of Himalaya, okay, using different sets of DEM. So this is again a chart or table which shows total area, orientation, maximum minimum elevation, and latitude, longitude, basin region, and glaciers. So how different types of studies are there, like direct glaciological method where it is done, hydrological method where it is done. So all these informations you can collect from GSI. They have got a good inventory of all those informations. So similarly, this is a plot again taken from Bhanu Pratap and his team's paper, where they have shown that how mass balance of each of these individual glaciers are varying, okay, from 1975 to 2010. So it's not necessary that all the measurements are continuous. Many are discontinuous. Some were done in 1975 to 1990. Few were done in recent time. Okay. So again, I said that why we need to study, estimate glacier mass balance. See, glacier actually it depends on temperature. It depends on temperature as well as precipitation in the form of snow. If temperature rises, if it goes above 0 degree centigrade, so what will happen? It will trigger melting. So therefore, what happens that the health of glacier is one of the most essential criteria or window condition that show us change in climate. If you really want to tell about climate change, then maybe the glaciers are the best indicators. Glacier are the best indicator, and indirectly it impacts the discharge also. And since it directly impacts discharge, And from discharge data also, we can indirectly infer about the climate change fact. So glaciers could be studied by change in length as well as change in area. Many people have done studies on length change as well as area change. Okay, but again, length change and area change, these are some indirect and delayed response to climate change, and which depend upon specific glaciers response time. And this response time can vary from few years to several decades. So therefore, maybe glacier length and area changes are not an ideal way of finding out the response of climate change. Okay. On the other hand, glacier mass balance, it's undelayed, it is unfiltered, and it's a direct method. So if you apply glacier mass balance, maybe you are getting a direct signature, and you get to know that what exactly is happening with that particular glacier, and it's a direct signature of climate change. Why? Because it reacts to change in winter precipitation as well as summer ablation. Okay. History of glacier mass balance studies. So if you look at the history of glacier mass balance studies in the modern era, so maybe it could be attributed to a Swedish glaciologist, H.W. Ellman. Okay, so H.W. Ellman, he is a Swedish glaciologist. So in the Nordic countries, he did ground-based measurement of accumulation and ablation for various glaciers, and that was during 1920s and 30s. So perhaps he is the first modern era person who have done some amount of studies on glacier mass balance in Nordic countries and between 1920s to 1930s. The first glacier mass balance study on the glaciological method means field-based method. It was initiated by the Geological Survey of India, which is a pioneering institute or one of the main institutes in India, which is doing lots of survey in terms of geology, mineralogy, geochemistry, land use, land cover, geomorphological changes, as well as glaciological studies. So GSI, they conducted study in 1974 of Gara Glacier in Himachal Pradesh. So maybe that is the history of glacier studies both worldwide as well as in India. So now let's come to the different systems like mass balance. What is a time system? So mass balance means the change in mass, okay, either positive or negative with respect to certain time, isn't it? With respect to certain time, we can say in 1 year, 2 years, 5 years. So how we actually find out mass balance? What is a time system? If you look at the time system or temporal system, so there are different categories. One is stratigraphic system. What is stratigraphic system? This is also known as natural mass balance here. So in this method, mass balance is estimated at an interval of a year when glacier mass is at the minimum. So it means you will have to track that particular glacier either from remote sensing technique or from some other technique to find out when the mass is minimum or when actually ablation period is towards the end, maximum melting has taken place. So that time when the glacier mass is at the minimum, this survey starts. Okay, so but this needs stratigraphy of snow to estimate minimum, and this could be different than calendar year. So stratigraphic system could be different than calendar year, as well as it could be different from glacier to glacier. If you are using satellite image to find out the stratigraphic system, it's a bit difficult because of the cloud cover. Most of the time the images could be cloud covered during that time when there is ablation taking place, because of which chances are very less that you are getting the minimum snow cover or the ablation period, the peak of the ablation period. Okay. Second method is called as fixed date method. Fixed date method starts from like 1st of October or September 30 is used to estimate mass balance. And this does not require any attention to stratigraphy of snow, and it relies mainly on mass change between fixed dates. So here we are assuming that whatever mass changes are taking place, we are spreading it across 1 year. So it doesn't matter whether we are considering it stratigraphically, it means when it was minimum. Rather, we are considering any two permanent time from 1st October to 30th of September. So during that time, we are actually finding out the mass change. Third method is called as floating date method. So floating date system, here the mass balance here is defined by the calendar dates of the two successive surveys, which may vary from year to year and may or may not be 365 or 366 days apart depending on leap year. So floating date system depends on where exactly we are going for survey, and we consider that as the time from where we start for the next survey date, and in between whatever changes are there, we are actually recording that particular change, and that change may not be year to year, it may be a year to year. Okay. Then there is a combined method. So combined method means it could be a combination of stratigraphy, fixed date, floating date system. So you can combine all these things together. So that is what is the time system of mass balance estimation. So if mass balance, so what exactly mass balance gives us? So from mass balance, we can infer that either it could be negative or it could be positive, or there could be zero mass balance. What is negative? Negative means glacier gets smaller. There's a retreating phenomena, or the glacier gets smaller, or the mass is decreasing. Okay, amount of ice means equivalent water is actually decreasing. Positive mass balance means glacier is getting enlarged, or it is enlarging. So there is an advancing of glacier. Okay, so it is enlarging or mass is increasing. So positive mass balance, it means area above the ELA increases. Negative mass balance means area below the ELA increases. It means in positive mass balance, the accumulation zone increases. In negative mass balance, the ablation zone increases. ELA here stands for equilibrium line altitude. Okay, and this equilibrium line altitude is actually an imaginary line along which mass balance is zero. We estimate that the mass balance is zero. It means whatever is the input will be the output. Okay, amount of precipitation in the form of snow, whatever is coming, that much is actually melting also. And then there is a zero mass balance condition, which is a balanced condition. So balanced condition means there is no change in glacier size, both in terms of mass as well as in terms of volume. Okay, but the glacier is still moving. Okay, zero mass balance does not mean that a glacier will be static. Rather, it is still moving, but actually it's a balance in this way that amount of snow or ice which is accumulating, equal amount of snow and ice is actually melting, and therefore there is a balance, steady state condition. So mass balance terminologies, and then we will go for methods for mass balance monitoring. Okay, so mass balance terminologies, there could be difference between accumulation of snow in winter and ablation of snow and ice in summer, and this difference. Okay, so what is mass balance? So mass balance means there could be a difference between accumulation of snow in winter and ablation of snow and ice in summer. This difference is called as mass balance. So here it's the summation of from T1 to T2, that is time 1, initial time to time 2, where we find out accumulation plus ablation. How much accumulation is done plus how much melting has taken place. So net balance, whatever is across the glacier, that gives the mass balance. Here when I say that accumulation of snow in winter and ablation of snow in summer, so that's not technically always correct. Accumulation is maximum in summer, winter. Okay, although there is little bit of accumulation which will still take place in summer, but that is insignificant. Similarly, ablation is also a continuous process, but in winter ablation is less, in summer ablation is more. Okay, so that's what is definition of mass balance. So as I said, T1 and T2, these are the initial and final time. B mass balance is the mass balance of a specific glacier. Okay, we are talking of a specific glacier, and unit here is meter cube water equivalent per year. Okay, or per annum. So meter cube water equivalent. Here we are not talking about the ice or snow. Rather, we need to convert it into water equivalent. How we convert it into water equivalent? Simply you multiply it with the density of ice. If you know the density of the ice, if you multiply it, you will get water equivalent. So meter cube water equivalent per year. Okay, or millimeter water equivalent per year. Such that water WE is water equivalent. Accumulation. What is accumulation? Accumulation is caused due to snowfall, deposition of ore, freezing snow, rain, solid precipitation, gain of wind-borne blowing snow and drifting snow, avalanching, basal freeze, or internal accumulation. So there could be many processes which can contribute to accumulation. For example, if there is snowfall, that's one of the most important. If there is deposition, there could be even avalanching also, which deposits on that particular area, that can also contribute to accumulation. Freezing rain, if there is rainfall which is freezing, that can also contribute to accumulation. Solid precipitation, snowfall basically. Then gain of wind-borne blowing snow and drifting snow. So if there is huge wind, generally it is not there in Himalayan condition, but in polar condition you could see that thing, that because of gush of wind, so that wind, what it will do, it will drift the snow and it will deposit snow somewhere. So that can also contribute to actually accumulation. Avalanching, if there is any avalanche which falls on the glacier, that can also contribute to accumulation. Then basal freeze and internal accumulation. Okay, so these are few of the causes by which accumulation can take place. Next comes ablation. So how ablation can take place? Ablation can be caused due to melting. Okay, essentially it can be because of melting. Second is calving or carving. So what is calving? It's like similar to like icebergs. You might have heard that many times iceberg from Antarctic or Arctic, they get separated out. They floats on the sea or ocean, and that's how actually the size of huge chunk of ice sheet or in Antarctic or Arctic, they are decreasing. So you might have seen the movie Titanic also, where a huge iceberg, it collided with Titanic, and that caused the downfall or the destruction of the whole ship. So similarly, it could be icebergs which get separated, or it could be even calving. Okay, in Himalayan condition, you can see calving also. So where you can see is calving if you go to Samudra Tapu. The name Samudra Tapu came from the word, there is a huge lake in front of that particular glacier, at the snout of that particular glacier, and in that particular lake you will see lots of calving, okay, snow chunks which are floating. So that is because of variable mass balance as well as because of variable velocity of the glacier also. Loss of windborne blowing and drifting snow, avalanching and sublimation. These could be few of the causes of ablation also. Change in mass balance could be important indicator of climate change, as absolute values can be influenced by local geomorphology of glacier and terrain. So although change in mass balance all along the Himalaya, it's an important indication of climate change. However, the typical changes within the glaciers, if you see each of the individual glaciers, typical changes are because of topographic condition also. So topography plays very important role. General role is played by the climate, okay, regional climate as well as dynamics of climate, and local influence is the topography or the terrain. So as I said, if I now summarize it, accumulation and ablation. So accumulation and ablation can take place because of snowfall, wind drift, avalanches, resublimation and condensation. What is resublimation? Sublimation, as you know, it's a process in which suppose there is a ice, okay, and there is very less temperature, especially in polar condition. So that ice, rather than melting, it will directly convert to what? It will directly convert it to moisture or water vapor. Okay, so that process is called as sublimation. It means there is a phase change. So there is a phase change, and the phase change actually it indicates what? It indicates latent heat. Okay, whatever heat is reaching, rather than increasing the temperature for melting, okay, so rather it is converting to latent heat. Then condensation. Okay, condensation is also one process by which accumulation and ablation can take place. So here resublimation means from vapor it will directly convert to ice. Surface ablation processes include melting, snow drift, ice avalanches, calving and sublimation, as I explained in detail earlier. So other variables that appear most often in mass balance studies, what are the other type of terminologies that we use in mass balance studies? So one is density. Density is very important because if you want to get water equivalent, WE, if you want to get water equivalent in meter cube, it's very important to know the density of ice or snow or fern, whatever is there in that particular area. Then only you will come to know about the water equivalent. Otherwise, suppose in area thick ice melted. So it means if it is thick ice which is melted, so more water will be contributed. If same volume of snow melts or fern melts, less amount of water will be contributed. So therefore, it is very important to find out the density of snow or ice or fern, so that we can exactly tell that how much water equivalent is there. Ice thickness. We should know the thickness of the ice, okay, where exactly we are doing the study. S is the area, okay, the area of the glacier is denoted as S. V is volume. AAR is accumulation area ratio, which I'll explain later on. ELA is equilibrium line altitude, and ELA indicates that particular line along which there will be what? There will be zero mass balance. It's an imaginary line where there will be zero mass balance. Okay. So vertical mass balance profile or VBP. What is VBP? If you look at this particular sketch here, you will see that this center line indicates zero mass balance. Towards left, it is negative mass balance. Towards right, it is positive mass balance. B here indicates mass balance. Okay. So what it says, vertical mass balance, that mass balance is calculated for individual altitude interval, and the mean specific mass balance can be depicted as a function of altitude, showing the vertical mass balance profile. So it means the mean mass balance or the specific mass balance in each altitude. Okay, if you divide a glacier into different altitude ranges, 50-meter altitude ranges, so what you will see, if you plot it, that in each 50-meter what type of behavior is seen. So along the body of the glacier, a longitudinal profile, if you draw along that longitudinal profile, the mass balance will be, initially it will be negative. Initially it will be negative. Here it is zero. This is the equilibrium line of that particular glacier, and then it goes on increasing. Okay. So what type of relation it is? This relation is exponential. Exponential means initially there will be negative, and slowly it will convert to positive, and then it will exponentially increase as we move towards the accumulation zone. So the relation is exponential. It means the vertical mass balance profile along the longitudinal profile of a glacier is exponential in relation, and 0 here it indicates the ELA, equilibrium line altitude. Okay. So mass balance spatial consideration. What is a spatial consideration? If you look at any such area, okay, any such snow covered area, I'm sorry, so you will find that this particular area, the upper part is accumulation zone of glacier, where the plus sign indicates positive mass balance, and this particular line is equilibrium line altitude. Okay, here the mass balance will be 0. It means amount of ice getting into that particular system equal to amount of ice which is melting. And then the lower part is ablation zone of glacier. So these are the differentiation of a glacier in spatially. Okay, spatially how you can differentiate. Mass balance here. So let's understand this particular figure. This figure, it is taken from Patterson 2000. It's a very nice book on physics of glacier. You can always go for this particular book. This is a classic book. Okay, this is a classic book. It has got lots of information. Although there are many nice books which are coming up, you can go through those books also. But I like, for a beginner, it's a nice book. So if you look at this particular figure here, you will see specific mass balance. Specific mass balance means what? Mass balance means mass balance across the glacier. Mass balance means the total amount of ice or snow which is accumulated minus what is ablated for the whole glacier. Okay, that is specific mass balance. So that is mass balance. When we say specific, specific means in along one point. At one point, wherever we are putting a stake, or if you are taking a small pipe or column along a glacier, in that particular point, what will be the specific mass balance? Okay. So here the T1 and T2 indicates different time period. T1 is initial time period, T2 is the end final time period. So this could be stratigraphic, or it could be fixed, or it could be anything. Positive here indicates positive mass balance, negative here indicates negative mass balance. The initial part indicates winter, the final part indicates summer, and this is the net balance. So as you could see, if we start from 0, so initially the glacier mass, it increases. Okay, so like if we start our survey from here, so initially if we consider that, okay, here the baseline is 0, from here the mass continues to accumulate as the winter progresses. As the winter progresses, the mass balance increases, and this line indicates accumulation. So why the mass balance is increasing? Because accumulation is increasing very fast. Okay, the slope of accumulation is very, very high. It means accumulation is increasing very, very fast. But on the other hand, ablation is very, very less. Ablation is negligible, and therefore net mass balance is more. This is the peak. Here it reaches the peak, and then the summer comes. When the summer comes, what will happen? That ablation will increase. See, here on ablation is increasing exponentially. It is increasing exponentially, but accumulation is almost flat now. Okay, although it is not 0, but it is almost flat, close to 0, close to flat, and therefore there is less accumulation, more ablation, and therefore again it goes down. Again it goes down. So initially it goes up, then it goes down. In between, if there is positive mass balance, it means whatever mass was acquired during winter, that much mass was not lost during summer, and therefore mass balance is positive here. Okay, otherwise if it comes here, it will be negative. These lines are shown as smooth lines. These are not smooth lines. Rather, there will be lots of spikes depending on when exactly snowfall took place, when exactly the climatological phenomena changed, radiation budget changed, or cloud cover changed. So depending on, there will be lots of spikes. This is not uniform. So fine, we have discussed the basic terminology. Now let's go to methods for mass balance monitoring. How do we actually do mass balance monitoring? Okay. So methods for mass balance monitoring could be divided into different types of sets of processes, like glaciological method, geodetic method, hydrological method, AAR or accumulation area method, or improved AAR, then energy balance method. So there are different types of method. It depends that which one suits anyone's requirement or that particular area. We can choose any one of them, and then we can do study. So glaciological method is a field-based method. What it requires? It requires site accessibility. It means, see, glaciers, wherever these are located, the places are very, very remote. Unless Ladakh, in Ladakh, you can see glacier at roadside itself. But in other places like Uttarakhand, Himachal, Sikkim, or even Arunachal, if you go there, you will find that the glaciers are located in remote area. You need to go there by trekking, and sometimes even roads are not available. So sites to be, accessibility is important. Stake installation on the glacier bed, high density network of stakes. So for glaciological method, you need to put some stakes, which are the poles, which we actually put on the glaciers, and these are our measuring bars. So you should have site suitability for putting the stakes also. At the same time, the stakes should be equally distributed. It requires minimum one field survey to install those and another field survey to measure the changes. Advantages are these are field based, therefore we could say that these are highly accurate, and these are sub-meter to sub-centimeter, okay, accurate if you are using DGPS, or it can go up to millimeter scale also if you are using DGPS. But these are point-based measurement, okay, we are measuring only at one particular point, which is specific mass balance. Limitation is it's intense manual labor. It means you should be a very tough person if you are doing glaciological measurement, so that you can go there by walk, you can do all the field survey. It's highly costly, okay, it's very, very costly. Why it is costly? Because fielding to those, if you are going on field to those glaciers, these are very expensive, because you need to carry lots of porter, lots of food item, generator, and even porters, high altitude porters are very, very costly. If a local porter costs you 360 rupees or 400 rupees, they will charge you some 1,000 rupees or 1,200 rupees per person. Why? Because it's a very high risky job, and it's a government approved rate in Uttarakhand. So high manpower cost, it's time consuming, it takes lots of time. Limited accessibility in rugged or glaciarized terrain. You can target only one glacier maybe, or 2 or 3 glaciers maybe in a year, not more than that, it's not possible, okay. But it's more accurate because we are getting field data. Geodetic method, sorry, next comes energy balance method. This one, energy balance method, here we need what? We need data on energy balance component, like we need data on rainfall, on snowfall, on temperature, wind speed, humidity, incoming solar radiation, short wave as well as long wave, outgoing solar radiation, short wave or long wave, from where that we can find out the net radiation. Okay, so you need AWS, automatic weather station, to be installed near to the glacier. Meteorological parameters for estimation we need, as I told earlier, and one field visit or more than one field visits are required, because you need to collect those AWS data frequently. Okay. Advantages, you get hourly temporal data available. So every hour you can find out mass balance, and it is useful for understanding physical process on the glacier. See, we can understand any physical phenomena by different type of processes. Like when I talk about this thing, what is science? Okay, what is science? What is technology, or what is scientific research and technology? So scientific research means when we are trying to find out a fact, we try to understand a fact, or we try to understand a process. Fact may be how many glaciers are there, what is the size of glacier. Process means how the glaciers are melting. Then you can even go for developing methodology, like how better we can measure mass balance, what are the different methodologies that we can develop. Or you can go for modeling. Modeling means if you can simulate the whole scenario, either in computer or in your lab, okay, considering the boundary condition. Within a boundary condition, whether you can simulate that whole process, this is called as modeling. And then forecasting, you can go for forecasting also, that what will happen in future. So scientific research, any scientific research can have any of this combination, any of these component or multiple components. Like it could be fact finding, it could be process understanding, it could be methodology development, it could be modeling, or it could be what? It could be even forecasting. Okay. On the other hand, technology. So in scientific research, what we do, we discover. Basically, we discover, and therefore we publish our paper in reputed journals like Nature, Science, or any other journal of your interest where your paper, work is fitting well. Technology, on the other part, when we talk about technology, so technology here essentially means what? That we are actually creating something which is non-existential in the nature, something which is not existing in the nature. For example, I'm using mobile phone. This is not natural. This is created artificially, which was not existing in nature. So this is a technology. Why? Because we have created something which is absolutely new. Or what you can do, what you can also technological part, you can create some software also, you can create some programs also, you can do some coding also, because coding, programs, softwares, all these things are actually something which is not existing in nature. you are creating artificially something, and therefore these are part of technology. So in technology we invent, and therefore we go for patent. In science we discover, therefore we go for research. In glaciological studies, either you can go for scientific research or you can go for technology development. It depends on your expertise, where exactly you are moving. Okay, where you are moving. Like I could see that there could be many engineers here, there could be many scientists also there. So doesn't matter whether you are a scientist or an engineer from science background or from engineering background. You can choose your domain, or you can choose your interest, whether you are going for scientific research or technological research. Both has got lots of application in glaciology. Limitation of hydrological or energy balance method is it's a point glacier melt measurement, because it is AWS location based and it has got a spatial coverage. Next comes geodetic method. Okay, here we need digital elevation model of two different time frame for thickness calculation, and it could be multi-annual measurement, average of specific mass change. Okay, and then here the problem is lack of information about seasonal correction and wide time scan. In detail we will discuss. Then accumulation area method, then hydrological method. So I'm not going in detail in this slide, but in future slides it will be discussed. So glaciological method, to start with glaciological method. So what do we do in glaciological method? Glaciological method could be also called as stake-based method. Stake-based method means you have stakes, which are basically poles. You carry those poles, you put it in a glacier, mark that point, okay, in some specific location in that glacier, mark that particular point, take measurement in your DGPS that what is the latitude, longitude, and its height. These three information you are taking. And then you are spreading such type of stakes all around the glacier. It should be there in accumulation zone as well as in ablation zone, and preferably in different elevation zones, so that you have a nice distribution. And maybe in later time you can go there and you can find out that how much in that particular area movement has taken place. Okay, how much movement has taken place, because the glacier will move. Second is how much mass has accumulated, how much mass lost. So all this measurement we used to take. So the integration over time of the mass balance rate at any specific point here indicates the stakes on the glacier surface gives the net mass balance at that particular point. So mass balance at one particular point is integration of 0 time to time t. 0 time is when you start measuring to time t of what? Of mass balance with respect to time. How much mass is accumulated with respect to time. So that's what you are integrating, and that's what you are getting the net mass balance at that particular point. The spatial integration of BP over the surface area ds leads to the total glacier mass balance in meter cube water equivalent or kg. So here what we are doing, that if we want to find out mass balance of whole glacier, here you are getting mass balance of individual stake, here you are getting mass balance of the whole glacier. So what you are doing now, you are integrating mass balance of each of the stakes. You are integrating mass balance of each of the stakes. How? Because you have area, okay, stake is put in one particular location, and you are considering that particular elevation zone as one specific area, one specific surface area ds. So here ds means with respect to time as well as with respect to certain specific area. So each of these stake will indicate one specific area and the changes with respect to time. So if you integrate it, you will get for the whole glacier. And if you multiply it with rho is what? Rho is the density of ice, okay, or snow, whatever is there. So if you multiply rho with volume, change in volume, you will get amount of water equivalent, which is meter cube in meter cube or in kg. Okay, kg water equivalent or meter cube water equivalent. So that much you are actually getting the water equivalent. That's what we try to find out. I think it's pretty clear. Maybe I don't know how well I communicated, but it's a very, very simple process. The surface area corresponds to the horizontal projection of the entire glacier surface. So horizontally, the whole glacier surface is actually extrapolated from each of these elevation zone where stakes are put. So local measurement of relative changes in height and density by the snow pits on and or probing. So it's the relative to the stratigraphic surface, and stakes related to the ice where it is anchored. So this is one of the example. I have taken it from Azam et al. 2014. So Farooq Azam, he is one of the glaciologists who specifically is more interested in glaciological mass balance. He is a faculty in Indore. What his setup is like, here you could see that this is a snout of the glacier, or that point from where the glacier starts melting. This is a location where precipitation gauge is there, okay, gauging site for precipitation. Then these lines indicate contours along the glacier. Contours means the elevation, okay, the area of equal elevation. Then we have stakes. The small stakes indicate stakes in ablation, and the bigger one indicates stakes in accumulation area. So he has distributed stakes all along, okay. And here the units are snout position with respect to x, y, and z. It means lat, long, and altitude. Accumulation in meter water equivalent, ablation in meter water equivalent, precipitation in millimeter. So that's the different type of units or dimension. There could be many sources of errors in stake-based methods. So what could be the sources of errors in stake-based method? Stake-based measurements can have certain error, like the measurement in the stake itself. Okay, the measurement in the stake itself, which could be a human error. Second is density measurement. Okay, so if we are because we are taking one density value and then we are multiplying it to find out the meter water equivalent, meter cube water equivalent. But if density change, but density is not constant, it keeps on changing from top to bottom. So if there is any misrepresentation of density, your water equivalent will be misrepresentative. Representativeness of stakes, because wherever you are putting your stakes, it should be representative of the whole elevation band. Okay, if you put 3-4 stakes in one particular area, it should represent the whole particular area. So representativeness of the stakes is very important. Then representativeness of pits, wherever you are digging the pits, that should be representative also. Accuracy of map, what is the accuracy of map? And change in surface level, if there is any change in surface level. So all these things could actually lead to some amount of error in stake-based measurement. And if you arrest all these errors, then maybe your results are quite good. Okay, higher is the density of stakes, better you will have better information, or more accurate you will have data. Okay, so carrying out mass balance measurements, accumulation measurement, and ablation measurement. So this is one of the process in this particular thing. What they do, they used to dig one pit, and they find out the snow. Okay, the different layers of snow, wherever the snow accumulated, and from these color changes they can find out when there was ablation, when there was accumulation. Okay, so the net accumulation is measured by digging snow pits or coring in the area of a glacier where snow has accumulated during the period of investigation T1 to T2, and the amount of accumulated snow is measured in water equivalent or water mass per area units, and it is calculated from measured snow depths and the respective snow density. And the snow cover has to be penetrated to the last observation dates or horizon, either by digging snow pits or by taking cores with a drill. Either we can take cores or we can dig snow pits, but we will have to go to that depth where our initial measurement started. We'll have to get that particular layer. If you're not getting that particular layer, you can't find out the exact information. Okay, so in accumulation zone, any natural or artificial marking made at T1 will be buried by snow by T2. So generally, if we go to mid-latitude conditions, in mid-latitude conditions, there will be lots of dust particles which will get accumulated during ablation season. So if you can locate the dust particle hard dusty layers, that can indicate that above that, whatever fresh snow accumulated, so you can find out this stratigraphy. Okay, that dusty layer is the end of ablation. From there, the clean ice is the accumulation season. So it's easier in mid-latitude condition, but in lower latitude condition, like our condition, sometimes we don't get that dust layer, and therefore we need to put some artificial markers, some colors or some artificial markers. And this artificial markers helps in what? It helps to find out, actually, if you can get that particular color or that marker, you can see that, okay, this was the layer where we started in T0, and then above that it is T1. Okay, so carrying out mass balance measurements. So typically stakes are drilled into glacier in the ablation zone, and changes in surface level are measured against stake height. So like this is in T1, this is in T2, when T1 plus 1. So when actually after the second time when you went there, you find out the height here, you find out the height here. This indicates this is your ablation. This much ablation has taken place in ablation area. That's how you find out the ablation amount, how much ablation has taken place. It means that much melting has taken place. Okay, that much melting has taken place. And thickness change E2 minus E1 equal to ablation equal to thickness change multiplied by density. So if you know the thickness change and if you multiply it by density, you can find out how much snow actually was lost in the ablation zone. How much snow was lost in the ablation zone. Second is geodetic method. Geodetic method depends on two sets of DEM. If you have two sets of DEM, even if you have Survey of India topo sheets also, So in topo sheet, as you know, topo sheet has got certain information. What type of information? Topo sheet is a classified map which is three-dimensional. It means it has a z value also, which indicates the height also, and height is indicated by contours, or it could be indicated by benchmarks, or it could be even indicated by some points which indicate the height, okay, the elevation. So this point data or benchmark data are very accurate data because they are surveyed data. So from this point data as well as from contours, you can find out that how much elevation was there in that particular time when the particular survey of India topo sheet was created, maybe 60s or 70s. And if you find today's DEM, and if you create same resolution DEM in terms of spatial resolution, from there you can find out the mass change. You can subtract these two elevation models, and then you can do mass balance or mass changes you can find out. Then again, here also there is an assumption about density in Fern and ice are critical. So here also your density is very, very important, that how much density you are considering. If your estimation of density is wrong, so your water equivalent will be wrong. And it's very easy to actually say about geodetic mass balance, there is simply subtracting two DEMs. Rather, it needs lots of correction. There are lots of error estimation. There are lots of adjustments. So people who are working on remote sensing, they'll come to know that what are the different types of tricks and processes to get exact mass balance. Okay, it's not that easy. Similarly, you can have different type of data source like photogrammetric, LiDAR, topographic maps, terrestrial surveys. Like now, there are many techniques. You can take laser scanner and you can take scanning of one particular area. You can even use topographic cameras also. From topographic cameras also, you can create 3D. And if you go in two different seasons, you can find out the mass balance. Okay. Yeah, and here actually the mass balance is computed for the whole glacier. It's not computed for specific area, rather it is computed for the whole glacier. And it could be used to periodically reassess the measurement from the direct glaciological method. So this is not substitute, but this is actually complementary. This is complementary or supplementary to the glaciological method. How? You have stake-based method, and above that you are putting geodetic method, and then you are getting the results because you can do it more frequently, or even in more time scales also, and you can actually complement your result. So this is one flow chart which indicates that you have DEM of T1 and you have DEM of T2. You do pre-registration of DEM, both of them should be of equal spatial resolution. Then you should do DEM error and bias correction. Preferably they should be of same season, maybe ablation season. After DEM error and bias correction, you should do elevation difference of DEM like T1 minus T2. Then from there, you have the glacier area, which you can collect from GLIMS or RGI boundary. From there, you can find out the glacier volume. In volume, if you put glacier density, from there, you can get glacier mass balance change. So this is one way of doing geodetic mass balance study. Hydrological method. So hydrological method, as I told, it was done for Siachen Glacier. Maybe there are very few works, or it was one of the reported work where hydrological mass balance was carried out. Here, actually, it's the subtraction of net precipitation in the basin at different elevation zones from the net meltwater runoff. So, what is the net precipitation and what is the net meltwater runoff? So, the difference gives us the mass balance. So, here, L indicates liquid water and IL indicates change from ice to liquid water. So, mass balance equal to total amount of precipitation in form of liquid water, total amount of evaporation in form of liquid water or condensation in form of liquid water, minus rainfall in form of net runoff, okay, outflow minus inflow in form of liquid water, and then plus FIL, which indicates melting of ice and snow. Okay, it gives total mass balance. From there you can find out total mass balance. So even JNU people, they are using hydrological method to find out mass balance. You can go through the papers or literatures to know more about hydrological mass balance processes or what type of instruments they are using. Then comes AAR based method. So AAR based method, maybe it was in 80s it was proposed that AAR based method could be one of the important way of finding out mass balance. So what is AAR based method? It essentially indicates accumulation area ratio for zero mass balance. So it means how much accumulation area is there with respect to mass balance. So a plot is created. From the plot you get a slope, and from the slope you find out the ELA. From the ELA, if you find accumulation area is more, then positive mass balance or negative mass balance. So In India, Professor Kulkarni, who is a professor at Nivecha Center of Climate Change in IIT Bangalore, initially he was a scientist at SAC Ahmedabad. He initiated these studies on AR based and specific mass balance based relation. Okay, estimation of glacier in the Indian Himalaya, and his study reported 0.44 AR for zero mass balance. Okay, he indicated 0.44 AR for zero mass balance based on regression analysis for the Western Himalayan glaciers. In 2004, he developed a regression equation by using AR and specific mass balance regression relation, where R square of around 0.89 was achieved to estimate the mass balance in the Indian Himalaya. And this was the equation which he got finally, where Y is the specific mass balance in meter water equivalent, and X is the AAR. Here the X indicates AAR, accumulation area ratio. And this regression equation between AAR and specific mass balance, it was derived from in situ. Where from that particular regression equation was derived? It was derived from the GSI. They collected information on Sean Garang Glacier between 1976 to 1984, 82 to 88, and for Gor Garang Glacier in Baspa Basin from 1976 to 1984. From those data, actually he used those data to find out this regression analysis. So this is Sean and Gor Garang glaciers. Here you could see there is mass balance. It is plotted in this axis, y-axis, and here accumulation area ratio is plotted. So when you have accumulation area ratio and mass balance, you get regression data, and from the regression data you can find out that AR equal to accumulation area by total glacier area, and Baspa Basin AR of zero mass balance equal to 0.5, and North America and Europe zero mass balance is calculated as 0.7. Okay, so here AR means accumulation area divided by total glacier area. So for that, actually we need long time series are needed for a calibration, and ELA or AR are estimated by remote sensing, which is only possible if snow line at the end of season equates to the equilibrium line. So generally it is presumed that when the snow melts, okay, during ablation period the snow melts, so it will reach to the minima. That particular minima in Himalayan condition, it indicates the equilibrium line. That indicates the equilibrium line. That is considered as the equilibrium line. And in between whatever snow line is there, it is considered as transient snow line. So hypsometric curve shows a variation of AR with respect to ELA. And AR EL equal to 1 by total area summation of ELA to top of the accumulation area, as that is the actually that particular change in area in the particular zone. So here, what is hypsographic curve? Hypsographic curve or hypsometric curve generally is a cumulative area versus elevation plot. Cumulative area versus elevation plot. From there, they found the AR based method. So this is a standard AR based method which was used for Chandra Basin, and I would suggest you go through two important papers. One was by Saili Taure and Anil Kulkarni, which is in Current Science, where they have discussed about the AR based method, maybe in 2012. It's a very nice paper on this particular method. It was published in Current Science. And then second paper, it was published in Annals of Glaciology, where an improved AR based method was published, okay, by the same sets of authors. So you can go through those papers if you want to know this particular method. It's a very interesting method. Only thing is we need field data also. It's not extensively remote sensing. We need field data also. What type of field data we need? We need AWS data. So if you have any AWS automatic weather station located nearby, from there actually if you get those data, you can use it for AR based method. And the general method for finding out melting, okay, during ablation periods. So melting could be estimated by temperature index method. So temperature index model could be used for finding out the melting. What is temperature index method? I think many of you are even civil engineers also. Maybe you have used wind SRM, okay, snow melt runoff modeling, or you could have used snow mod also. So there are many snow melt runoff models which are based on temperature lapse rate, or which are based on temperature index. Temperature is considered as one of the important parameters based on which melting is estimated. These are mathematical or statistical models. These are not physical models. So this is also a type of mathematical model or statistical model where you have certain amount of input from ground also. Okay. Third is the energy balance method. So energy balance method means, see, idea is very simple. Either you can study any process or any fact or any phenomena using from physical point of view, okay, in nature, or mathematical point of view or statistical point of view. When we say physical point of view, we presume that everything is driven by some physical processes, okay, which is true even for glacier also. How glacier will melt? Glacier will melt only in few conditions. If there is less precipitation, mass balance will be negative in few conditions, like if there is less precipitation, or there is more increase in temperature, air temperature and surface temperature, or there is some change in radiation budget. Okay, so in these three conditions you will have melting, or mass balance will be negative. Okay, so basically it is driven by the radiation, as well as it is driven by temperature and rainfall and humidity. Okay, so if you analyze these parameters, you can find out the physics. You can find out the physics, which is your process understanding. Process understanding is basically energy balance method. If you are using statistical method, so from energy balance also you can do modeling, okay, but statistical method is mostly it's purely modeling only. Why? Because you have certain amount of data, you are plotting it, you are trying to find out any statistical relation or mathematical relation, and from that particular relation you are actually extrapolating, or you are using that same relation in some other area also. So that's statistical. You are finding out a pattern. Here you are not concerned about the physical process, you are more concerned about the statistical process. So now the energy balance method, it depends on the physical processes. So I'll show you two case studies where we have used physical based model, okay, to find out glacier mass balance, and one among them, it is based on GRACE data. GRACE is a satellite data which measures change in gravity, okay, change in gravity. So glaciers of high mountain Asia are considered a natural climate meter to understand sensitivity of climate change. However, the altitudinal variation and complex topography limits the field-based mass balance observation in this region. So therefore, there are many studies using gravimetric data, or GRACE data, or gravity data in polar region. Like in Antarctic or Arctic, you will get lots of good papers on GRACE data in its application for mass balance studies, but in Himalayan condition, it is less used. The reason is that GRACE data has got very poor resolution. Okay, the resolution of GRACE data is very poor. It is in degrees, not in meters. So degree, you know, 1 degree is 112 kilometers at equator. So you could see that how poor the spatial resolution is, and therefore maybe if you target individual glaciers, it is little bit difficult, and maybe that could be one of the reasons for which gravimetric data was not used. But we tried with some modification and few corrections to find out mass balance using GRACE data. So the study site, as you could see, could be divided into 4 zones: Karakoram, Western Himalaya, Central Himalaya, and Eastern Himalaya. And these boundaries are not sharp. However, these boundaries indicates different type of climatic zones. Like the Karakoram, it has got completely different climatic zone, different type of precipitation forms or seasons. Western Himalaya mostly influenced by western disturbances or westerlies, and Eastern Himalaya mostly influenced by monsoon. Central Himalaya influenced by both. Okay. So the Karakoram region, it records around 32,399 glaciers outlined, which covers an area of 42,000 square kilometer out of total area of 7,13,907 square kilometer based on RGI 6.0. Okay, according to RGI boundary. Again, these boundaries, okay, glacier boundaries, it depends on what scale you are mapping. At what scale you are mapping. So depending on if your scale is very large, it means you are mapping small area, so you will have more glaciers. If scale is small, so you can target only larger glaciers. So similarly like that. So RGI is one of the standard data which was created. Okay, random glacier inventory, it was created. Why it was created? So that the input or this the output could be used for IPCC. Okay, to actually find out the impact of climate on glaciers. They use these outputs. Therefore, this was created. So here the area of the glaciers covered was 21,683, 8,389, 8,947, and 2,983 for the Karakoram, Western Himalaya, Central Himalaya, and Eastern Himalayan region. So Karakoram had more area compared to others. Data sets that we used. Here we used GRACE data. So GRACE data, basically what it gives here, it's a process data. We have not used raw data. We have used, so GRACE is based on your satellite data, where twin satellites, 2 satellites were launched, which are called as Tom and Jerry. Why these were called as Tom and Jerry? Because each of the satellites used to chase each other or follow each other. They are separated by certain distance, and that distance is measured by microwave beams in K frequency, and actually if there is any change in their distances, okay, if there is any change in their distances, which is mostly influenced by the gravity change in the earth, because gravity may have certain amount of pull impact on that particular satellite, so there will be some amount of changes in their distances. From there they try to find out the gravity anomaly, and from there actually terrestrial water storage was derived. Again, this was the TWSA data. These are actually provided by different libraries like JPL, Jet Propulsion Laboratory, then GFJet, then CSR. These are few of the different types of data sets which are available from different institutes, organizations, or universities. So what we did, we combined it together, and then we tried to actually get an average, because each of these data set has got certain amount of error or certain amount of difference in calculation. If you average it out rather than finding out the error individually, you can get a more compromising data sets, okay, more acceptable data set. The resolution was 0.5 degree into 0.5 degree, which is monthly. And GLIDA's data is a model data from both satellite data as well as satellite and station data also. From there, SMS and SWE, we snow water equivalent, and so we derive from GLIDA's. And the agencies or model is NOAA version 002.1. Resolution is 0.25 degree into 0.25 degree monthly. We used ERA data also. So ERA data is GLIDA's, it stands for Global Land Data Assimilation System. ERA data is actually a European Center for Medium Range Weather Forecasting Reanalysis data, which is ERA 5 land data. Resolution is 0.1 degree into 0.1 degree, and it's monthly. So here the variables are total precipitation, snowfall, air temperature, evaporation, total runoff, SWN, LWN, and duration was 2002 to 2019. Then from WGMS, mass balance, okay, time series data, and glimpse, we used Glacier outline data from RGI 6.0 version. And like if you are doing this study, rather than using ERA 5, you can also use IMD reanalysis data. So recently IMD also launched reanalysis data. Resolution is I think 7.5 kilometer or 12 kilometer, maybe something like that. You can just Google it, type it, you will get IMD reanalysis data that is specifically for Indian region. And it's a very good data actually. You can use that one also. Since this paper is a little bit older, so we used ERA 5 data. So when we try to find out the from hydrological year, okay, we try to find out the mass balance, okay, we try to find out the mass balance in each of these years. So this is average and of all years per month, and this is individual months. So other than the KK, all the regions, okay, Western Himalaya, Central Himalaya, and Eastern Himalaya were undergoing a negative mass balance change from 2002 to 2019. Okay, so here the mass balance here is, this is red is negative and this is your positive area. So this is your Karakoram area, then Western Himalaya, Central Himalaya, and Eastern Himalaya. Okay, the overall monthly and annual time series demonstrated that the maximum mass change occurred in the Central Himalaya, followed by Western Himalaya and Eastern Himalaya. So you can see here mass balance is positive in Karakoram, which actually quite well adjusts with the information by many other scientists, like it is called as Karakoram anomaly. In Karakoram, mass balance is positive. So in our result also the same thing could be seen. Here also it is negative, here also it is negative, here also it is negative. Okay, and here these lines shows mass change. The bold line, zero line is zero mass balance, and rest is your here it is negative, here it is positive. Okay, if you look at this particular. So here this particular figure is a very important figure. This indicates that total mass change monthly you can find out, yearly you can find out, average you can find out, and how much changes is taking place you can find out. And in Central Himalaya the mass change is maximum. Here the mass change is maximum. Yeah, to continue with, here there is a special trend of annual mass change with a significant level at 5%, and pixel wise area covered by glaciers, that is glacier area divided by grid area multiplied by 100. Okay, so that's how we try to find out. And here it is plotted. The zigzag line it indicates monthly, and the smooth line it indicates yearly, and this line it indicates the fitting. Okay, fitting Y of yearly mass change. So here you could see that for different for Karakoram, Western Himalaya, Central Himalaya, and Eastern Himalaya, what we can find out. Okay, and GAC here is your glacier area change. This indicates glacier area change. Here it is 10.5%, 26.4%, 13.3%, 6.2%. Okay, and this equation actually positive means slope positive means increasing. Here it is decreasing. Here it is here it is decreasing. Here it is almost it is constant. Here actually here it is almost constant. So you could see that here we can find rate of mass change. This is a hotspot. Okay, this is a hotspot. Again, here is a hotspot, but here it is a positive hotspot, and this could be also hotspot. So we could identify 3 hotspots, B, C, and D. 3 hotspots we can find out. Okay, which are plotted actually, plotted here. And pixel-wise area covered. Sorry, these plots actually, these plots are A indicate this, B indicate this, C indicate this, and D indicates this. Okay, then here it indicates pixel-wise area covered by glaciers. Average volume change, okay, gigaton per year. This also we try to find out for all the areas. This is pixel-wise, and this is with respect to each of the separate regions. Okay, here also we try to find out average volume changes. Then we also trying to find out, like we talk about glacier change with respect to GRACE data, how much melting took place, how much changes took place. Now we try to find out what are the physical processes or what are the forcings acting on those glaciers and how these forcings are actually changing the pattern of melt. So here it indicates mass change trend. Okay, Mann-Kendall change, the trend analysis. So how the mass change are taking place all over Himalaya. Air temperature trend, what is the trend in air temperature? Total precipitation trend, what is the total precipitation trend? Snowfall trend, then evaporation trend, total runoff trend, snow water equivalent trend, and shortwave, net shortwave trend, net longwave trend. Okay, so we these are the forcings, or these are the parameters which we use to find out the changes. And here you could see all the changes with respect to these parameters are analyzed. Like here it is snowfall, here it is precipitation, energy flux for different regions. Okay, A, B, C, D for these different regions. All these parameters are checked. You can go through this paper. It's a very interesting paper. Going through each of these variables will take a little bit of time. Therefore, I am shortening the process. Yeah, so the mass change was highly correlated with the total precipitation and snowfall variability over the spatio-temporal scale. And in contrast, this correlation fails at the location where evaporation, runoff, and radiation were causing mass loss by trapping the energy over the surface. Okay, so this was one of our findings. So what we concluded, that the estimated regional scale mass change will be useful for the socioeconomic aspect, as it provides a better understanding of future water supply in the downstream as well as the upstream region. And the spatial mass change will help in the identification of the hotspot, cold spot region, and further use for the basinal scale mass balance estimation. So this is a nice indication. Actually, from here you can find out if you have climatic data, if you have future data, just put your future data and you can find out the future trend also, that in future where this hotspot will be created and which are the regions which will be more impacted. Okay, so a very nice I think representation which can be carried forward in future also. You can carry it. Second most one more interesting thing is we developed one energy balance model for Sutri-Dhaga Glacier and that particular area. So incorporating the energy balance components, and this paper was also published, and this was part of, again, HICOM project. Both these papers are part of HICOM project. So what we have done, that for estimating the Himalayan glacier response to future climatic change in their impact in regional population, a reliable physical based model is required. Okay, which is called as energy balance model. So I already told you that what is physical based model, what is mathematical model. Physical based model means we are trying to find out the physical process. We try to understand physical significance, and mathematical model or statistical model means we try to find out a model based on statistics. Okay, its distribution. From there we try to find out some information. So here it's a in this study, hybrid method was developed by parameterizing the energy fluxes and input climatic variables. So from there we developed a hybrid model. So this particular model is based on the standard surface energy balance equation, which is indicated here, like FM is the net heat flux available at glacier surface, equal to Rn is the surface net radiation available at the glacier. HS and HL are the sensible and latent turbulent heat fluxes, and Hg is the ground heat flux in the snow ice. P is the heat supplied by the precipitation, which is small enough to be neglected in glaciers. And all energy fluxes are expressed in watt per meter square. Okay, it's expressed in watt per meter square. It means radiant flux. It's a radiant flux. So study area, these are the glaciers which are targeted, like Gepangat, Hamta, Sichum, Chota Shigri, Bada Shigri, Batal, Sutri Dhaka, Samudra Tapu. These glaciers were selected based on their area also. These are some big area. They are located in different orientations also. And we have some information, previous information also on this data. Field was quite easier for us because we were supported by NCPOR. They have a permanent station there. So they supported us because this was funded by NCPOR only. So here it shows elevation. This is a cumulative area elevation curve for each of these glaciers. The study area is Chandra Basin, and period is from 2013 to 2019, where we used 52 images. Okay, cloud-free images, Landsat images were used, where cloud cover was less than 10%. And Landsat 8 OLI remote sensing data and AWS data for calibration and validation of model we used for 2 different periods, 1st October 2015 to 31st October 2016, 1st October 17 to 18 October 2018. And it's a basin scale mapping. The data sets that we use are Landsat 8 OLI because of high resolution, 30 meter, AWS data like relative humidity, wind speed, etc. Station data, air temperature, incoming and outgoing shortwave, incoming and outgoing longwave albedo also from there. And ERA 5 land data where total precipitation and snowfall was actually estimated. You can also go for downscaling also. There are many methods of downscaling. Statistical methods are there, dynamic methods are there. So you can use either statistical or dynamic, whichever suits you. Fine. So this is a proposed basinal scale glacier mass balance method that we developed. Here, the beauty is like each of these components, surface albedo, incoming short wave, outgoing long wave, incoming long wave, most of these things were parameterized. Like albedo top of the atmosphere was parameterized from reflectivity data and spectral radiance data. Then atmospheric albedo we got, atmospheric transmittance we got from atmospheric pressure, elevation, latitude of the pixel and solar hour angle. So using standard equations, we try to find out or parameterize it. Solar incident angle we got from surface slope, aspect, solar hour angle, and latitude of the pixel. From there, we try to find out the solar incident angle. How and which equations we have used, please go through our paper. You'll come to know. Relative Earth-Sun distance is from the data, date of data acquired, so you can get it from your metadata. Then surface emissivity was estimated from NDVI, normalized difference in vegetation index, SAVI, and LAI, leaf area index. Okay. Then land surface temperature was estimated from average limiting wavelength of TIRS. Black body temperature at satellite was estimated from calibration constant, spectral radiance. Then we have surface emissivity. Okay. And then incoming long wave from atmospheric transmittance as well as modeled air temperature. Actually, we modeled the air temperature also using LST, NDVI, and albedo. So in one way, we actually derived all these parameters from satellite image, or everything was modeled using few of the best equations available at that particular time. And this is a basic energy balance model. I won't go through this thing. Simply, it's given here and it's very simple to understand. So from there, we try to find out turbulent sensible heat flux and latent heat flux. So why it is important? Like if there is certain amount of energy, okay, radiation energy, which is reaching to the glacier surface or any earth surface, either it will heat up the air or it will heat up the surface. Okay. So if there are no evaporation or sublimation, if there is no evaporation or sublimation, so what will happen? That heat will be absorbed and it will increase the temperature. And from that increase in temperature, more melting will be triggered. But if that heat is absorbed and then rather than increasing the temperature remained constant, rather that amount of heat was converted to evaporation or sublimation, then it is called as latent heat flux. So you need to find out sensible heat flux as well as latent heat flux. From there only you can find out the final melt. Melt was estimated from this particular equation. Okay. Final melt by LF into rho W. Rho W is the density of water, LF is the latent heat of fusion or melt, Fm is the available energy on the surface and will produce melt only when the surface temperature reaches 0 degrees centigrade. So for sublimation, if there is any sublimation, so like when the glacial surface is negative, then sublimation process derived using the latent heat of vaporization is based on HL by LV into rho W. Okay, and LV equal to 2.834 into 10 to the power 6 joule per kg. And this is standard value, and rho W is the density. So this was what was used to estimate the melt. So what we found for each of these glacier, different type of color for different type of lines, it indicates each of these glaciers. Even bar graph also indicates each of these glaciers. So we try to find out for each month how the your temperature and precipitation is changing, how temperature and precipitation is changing. Here the results are like what are the behaviors of energy fluxes, snowfall, sublimation. Okay, so for each of these glaciers we try to find out. All those actually different type of energy parameters are estimated, and like the average monthly RN was observed positive from May to October, otherwise remains negative for the rest of the year. And average monthly energy and mass fluxes of the selected glacier during 2013 to 19 are plotted here. This is altitude-wise energy and mass flux distribution. So in altitude-wise, how energy and mass flux distribution changes. And here different color indicates sensible heat, net radiation, net shortwave radiation, net longwave radiation, and latent heat. Okay, this is spatial variability of the energy and mass fluxes over the glacier surface. And for these are for two different date images, that is 6 October 2017 for ablation and 31 March 2018 for accumulation. Okay, these were selected. And this mean energy component were assessed at 500 meter ASL interval, elevation interval over the selected glaciers. The long wave net and HL flux becomes less negative as it moves higher elevation, whereas the HS flux, okay, short wave, and was not consistent for all the years. And short wave net shows the higher value at the upper elevation. Okay, and this was a comparison between the modeled and the observed TA, air temperature. We try to model the air temperature, and we had observed air temperature also. We try to find out the relation between them, and we could see a very good relation, because as I told that here we have used model air temperature. We have modeled it, and this is a correlation matrix which was plotted between the annual glacier mass balance and the glacier meteorological variables. So mass balance was plotted against all these variables. Okay, all these variables were considered here. The alpha shows a negative correlation with land surface temperature, while a positive relation with snow water short wave, okay, SWO, and a higher positive correlation was observed between RN and SWN. So overall, what we concluded is that overall the proposed model it has performed well with the observation data. The main benefit is that here we get a very high resolution information, and all these informations are modeled rather than downscaling. And Chandra Basin glaciers were losing its mass rapidly with a mean annual mass balance of minus 0.59 plus minus 0.12 meter, okay, water equivalent per year during 2013 to 2019. And RN is the main source of energy. Okay, net radiation is the main source of energy, which contributes about 75% energy to FM. Okay, for melting, whereas HS and HL, okay, that is sensible heat and latent heat, and HG fluxes shared 15%, 8%, and 2% respectively. Okay, and the proposed mass balance model can be useful for glacier-wide energy and mass balance at local as well as basinal scale. And the maximum mass changing glacier will be considered for the local scale mass balance estimation. So the work that I have presented here is a very, very detailed work on mass balance estimation using a new energy balance method. And the previous one was using GRACE data. So I thought that these two case examples can substantiate this particular lecture, that if anyone want to carry forward such type of work, you can do many things, okay, beyond what has been done in these two papers. There are many improvements that you can do. Okay, then we developed one snow water index also. Like for all these processes, you need to map snow cover. So a snow cover can be mapped in different ways, and there are many indices which are developed. What are the indices? Indices are actually some ratio images, and this ratio images are normalized. When we normalize in a ratio image, the value lies between +1 to -1. And why these indices are so specific? These indices are so specific because when we use multispectral images basically gives us separation, okay, separation between different objects, spectral separation between different objects. So multispectral images explore the fact that there is a spectral separation between different type of object, based on which you can develop n number of indices. So we developed one index which is called as snow water index. And why this was important? If we use NDSI, if we use S3, or if you use NDSSI, SII, they have certain problem. Like NDSI, you can't differentiate between water and snow. Okay, both of them almost show same behavior. So differentiating them actually becomes difficult. So limitation of NDSI is that in shadow condition as well as without shadow condition, you can't differentiate between snow and water. Okay, both of them shows almost nearby value. So both of them are classified as same. So study done by George Joseph and Navalkund et al. 1991. Then George A. Riggs, Dorothy Hall 1994-95, Kulkarni et al. 2002 and 2004. They all said that water bodies generally show low reflectance, but its NDSI value is higher. Because of higher NDSI value, it is always misunderstood as snow. It means when you use NDSI, you will always misunderstand water body as snow. So how you can remove that thing? Similarly, this is a comparison for SWI also. I'm not going into this thing. You can just go through the paper if you want to know more. So we tried to plot NDSI and SWI, and just to find out. Yeah. So we proposed one new index which is called the snow water index. This snow water index, it does what? It includes NIR. NIR is one particular band which helps us to separate between a water body with non-water body. It helps us to discriminate between water body and non-water body. So based on the inclusion of NIR in this particular equation, we could actually separate water body very nicely. Okay, like this first one. Okay, so in first one you could see this is using NDSI and this is using your SWI. So here you could identify the water body clearly. This is a comparison between NDSI and SWI. So I have just told the short form of the whole story. To cut the whole story short, SWI actually it helps us substantially. We have even used spectra, field spectra also that we got from both IIT Roorkee as well as from SASE, Snow and Avalanche Study Establishments. And using those spectra also, we have tried to use this particular our developed model or index SWI, and we could see that our model performs way better compared to NDSI. So like in future, if you are using any index for snow mapping, you can always go for SWI, and SWI I believe will give you much better result because you can always classify water body easily compared to NDSI. Okay. So that's what was crux of this whole thing. And thank you for your attention. And yes, I could end my whole lecture right in time. It's 1 hour 120 minutes. So it means 13:20. So now I'm open to questions. If you have any question, I'm open to questions.